Hey everybody, this is Mr. Ainsworth, and we're going to get into section 4 here of chapter 5 in Euler Circuit chapter. And we're going to talk about graph models here and how to model a real life situation in a variety of different ways. But let's first start off talking about the universal tracings that we saw in the very beginning of the intro lessons before this chapter even started. So let's read this together and give it a shot, okay? Starting at a given dot or vertex here, determine if you can trace all lines without lifting your pencil. Okay, that's important, without lifting your pencil. Or retracing the edges. Okay, so you can only trace the edges once. That's what that means. And end back at the dot or vertex, which is represented as closed universal tracing. Or if you end up somewhere different, okay, we're going to call that open. All right, and sometimes it's not even possible, so we'll say neither open or closed because you can't even do it. Okay. So let's start here. We're going to start where the big vertices are right here. This is our start. And this is going to be our start for this one. And this is going to be our start for this one, okay? So in diagram number 1, this you may do it this way. You can try it. You can pause the video if you like and try it, okay? And then replay it. It's always nicer that way when you can do it by yourself, but this is one possibility. If you choose just to watch and see a possibility for universal tracing, okay? You can go this direction here, this way. I'll put some direction on so you can see it. Okay, just follow the arrows and then come back down here. Ooh, that's not good. I didn't mean to do that, sorry. This way, that would have been a problem. So I'm going to go this way, this way. See, that's why you should use pencil. Okay, and then this way, over across here, and then down here. And let's go back up again. Let's just go around these rhombuses, okay? Rhombi. Ooh, we use a word from geometry right there. And then back up here, and then across. And then back up this rhombus up here. These are all congruent. And then back down. I'm not going to bother labeling them, okay? So just follow the arrows. And then come up here, and then back down, and then we're going to end up down here at a different point. Ooh. Okay, so we're going to end. I'm going to put the end right here. So check that out. We started up top right and we ended in the lower right. Okay, when that happens right there, when you end up somewhere different, we call that open. Okay, so let's classify this as open. Why? Because the start doesn't equal end. So start does not equal end point. All right, we call that open universal tracing. Now let's try this one. Again, if you want to, go ahead and just pause the video and give it a shot. It's more fun that way anyways. So I'm going to assume that you have already done that, so I'm going to go for it. Okay, so I'm going to just cruise around the drawing right here. Okay, this way. I'll put some direction on here so you can see my path. Come down here, so cruise across here. I'm going to go up a little bit. I'm going to cross this way. And gosh, I haven't done this before, so we'll see if this works. All right, if not, I just back up, right, and do it again. I'm going to come down this way. Now I'm going to cruise along the rectangle and down here and across and then up. All right, and then down. Ooh, and then back up again. And guess what? I ended where I started. Okay, right up here. And I knew that was going to happen. There's a way to tell by looking at these drawings where you start and where you end, by the way, and that's part of the of what we're going to learn later on. Okay, but I'm not going to spoil the surprise. Okay, so this one right here, if you end back where where you started, you call that closed. So this is a closed universal tracing. Why? Because the start equals end. Okay, so start equals end point. Okay, just look right here. We started there and we ended there, so it's closed. If we start and end at a different place, we call it open. Okay, and that's what those mean. So start, if start does not equal end, we call it open. Okay, if the start equals end, well, we call that closed. So these lines are a little bit different. These graphs as we call them in graph theory, just not the type of graph that you're used to. Okay, and then this one right here, you're going to start here. All right, and notice the degree 3 here. This is degree 3, degree 3, degree 3. 1, 2, 3, 4. This is 4, 4, and this is 3, and this is 3, and this is 3, 4, 4. Okay, there's 1, 2, 3, 4, 5, 6 degree 3s. 6 odds. 6 odds. Now, there's something about that, okay? And because of that, I know that this one's impossible. Okay, impossible to trace. Okay, so it's neither open nor closed. So neither open, okay, nor closed. Why? Because you can't do it. All right. I'm not going to spoil the surprise. I'm not going to tell you why, but I know it has something to do with the number of odd vertices versus even vertices, and that's part of the learning process through the chapters that we'll figure that out later. Okay, this section here, we want to figure out how to model real life with graphs, right? How do you take a real life situation and model it mathematically using a graph, with a bunch of vertices and edges, all right, and then you can analyze it. That's what Euler did back in the 18th century. So you're going to learn how to do it. All right, that's part of the goal of the lesson. So here, further classification of universal tracing with graph terminology. Okay, and we talked about two things. We talked about paths in the previous lesson, and we also talked about circuits. Okay, well, we understood back in the previous section that if a path is a sequence of adjacent edges right here, where you start at one place and end at another place. So a path is an open universal tracing. So a path, which is start does not equal end, is equal to open universal tracing. Okay, that path means open. All right, that means that let's put in parentheses here. Start does not equal end. So start does not equal endpoint. Okay, great. Now the circuit, okay, that like the one up here. Okay, and when we found out in circuits, you always start and end at the same place. So that refers to a closed universal tracing. So circuit in graph theory, all right, is the same thing as a closed universal tracing, closed. And that means the start must equal endpoint. Okay, so path is referred to as the same as open universal tracing. Start doesn't equal end. Circuit is a closed universal tracing. Start equals end. That's the connection between the two. And then what additional characteristics or requirements does what additional characteristic or requirement does a universal tracing have? Well, I'm not going to discuss that yet, so we're going to move on, okay? I'm going to hold off on that one. So, Euler path. A couple. These are big new definitions here. We're going to talk about what's an Euler path and an Euler circuit in this section. So, an Euler path. Okay, our first big one here. So, Euler path, and this should be in your Chapter 5 vocabulary list here pretty soon, because we are going to be working with these a lot. Okay, so an Euler path is a path that travels through each edge exactly once. Okay, so a path here that travels, all right, through each edge exactly once. Once. Okay, so an Euler path right there, start does not equal end. So let's make note of that. Start does not equal endpoint on a path. All right, but you got to go through each path once. Excuse me, each edge once. Okay, that's what an Euler path is. Paths in general do not have to go through each edge. However, an Euler path does. Okay, each edge once. That's a requirement for an Euler path. Now, an Euler circuit. Okay, an Euler circuit. Well, we just learned about up here that it's closed, start equals end. But this time, we say that Euler circuit is a circuit that travels through each edge exactly once. Okay, so a circuit now, all right, that travels through each edge. Notice how both definitions have that, each edge once. But this one, because I say circuit, Euler circuit is a circuit that travels through each edge once. That means that you have to start and end at the same place. So start equals end on a circuit. All right, but this is a special circuit. You have to hit each edge once. And in Euler path, you have to hit each edge once. But you're going to end up at a different spot. Okay, so there's the difference between the two. Okay, basically, since the two both involve hitting each edge once, you got to remember Euler means, when you see the word Euler here on a path, it means that every, okay, edge once. I want you to connect that in your mind, okay? Because it's not just any ordinary path. It's an Euler path or an Euler circuit where you hit each edge once. Every edge. You can't miss one, okay? No missing one. So these have got to be part of the chapter 5 vocabulary. So let's highlight these, okay? Right, this is big time important stuff right here, okay? Now, let's get into a little bit of modeling. Okay, this is let's go back to the very beginning. In the very beginning, when I started talking about the origin of graph theory back in the 18th century, somewhere in the 1700s, when Euler was alive, he heard about the seven bridges of Königsberg. Now, remember, there was a city called Königsberg in Prussia. Okay, now nowadays it's called Kaliningrad in Russia. However, back then it was called Königsberg, and they had this Prego River here, and it was cruising through the city, and it forked off and it went around a couple islands, and it had what was considered to be a right bank and left bank, and these islands A and D right here. So this river split and went around these, and then they had these bridges. Well, seven of them, right? It's called the Seven Bridges of Königsberg, and the people in Königsberg wanted to know. This is where it all started, right here. If it was possible to stroll through the city and cross each of the seven bridges once and only once. This is the original problem back in the 18th century. All right, and they searched and searched and searched for a solution, but couldn't find one, and there's a reason why too. Euler actually proved it. So first, though, in our case, we want to model word problems, okay, with a graph. And when I say model, you want to translate a real situation here with something mathematical. And sometimes it's a function, sometimes it's an equation, sometimes it's a set of numbers, sometimes it's an inequality. You know, it depends. Some situations like these end up being graphs, and then you interpret the graphs to solve the problem. So the first step that Euler figured out in terms of the modeling, all right, is we took the problem, this word problem here, and we created a graph which represented the city and the river and the bridges. Okay, so graph models identify what can represent vertices and edges to represent real life situations. So what we want to do in each problem when we try to model something is we want to interpret what represents the vertices and what represents the edges. So what Euler did, and let's put the bridges in here. There was one here, 2, 3, 4, 5, 6, and 7. Okay, there's 7 bridges right there. So, and he called this the upper bank right here. He represented it as a vertex, and the center island here is another vertex, and the lower bank is another vertex. So he got creative, and he did what no other mathematician did at the time, because they didn't think of it before he did, is he represented the land masses as vertices. Okay, so these represented land masses. Okay, and as such. And then what he did was he represented the bridges as edges. So the edges in his mind were the bridges. So he said, okay, well, I can travel from the right bank to the island this way. I can go this way. So notice the edges right there. I can go from Center Island across this bridge, or I can go through this bridge. And then I can get from the Center Island to this other island this way. And then I can get back to the upper right bank through this bridge, or I can go to the left bank this way. And notice what just happened here. If we take this graph that I just drew and recreate it, I've got 3 vertices. 1, 2, 3. 1, 2, 3, and then the fourth one is the the other island right down here. So I'm going to put that down here. And so he said, well, I've got 2 bridges here and 2 here. I've got 1 bridge here and another bridge here and another bridge here. And so the land masses are these vertices. All right, the land masses are the vertices. This one here and this one here, and the bridges, well, guess what? They're in blue, and they're right here. That's bridge. Okay, in real life. Okay, not the bridge that we talk about in graph theory, but I'm talking about just representing the bridge in real life here. Because remember, this is the seven bridges of Konigsberg. And then what he did was he studied this graph, and he looked at it, and he looked at the degrees on this, and this one's degree 3, this one's degree 3. 1, 2, 3, 4, 5. This is degree 5 right here, and this is 1, 2, 3. This is degree 3, and he studied it and noticed that there is something about a graph that has more than two odd vertices. And he formulated his Euler theorems, proving that this problem cannot be solved. It was impossible to stroll through the city and cross each of the seven bridges once and only once. It was impossible, and there's a reason why. You ought to try it. Try that. Try to trace it, and like a universal tracing, and give it a best shot. You're going to be working on it a long time, because people in Konigsberg did work on it a long time, and guess what? They were unsuccessful, and there was a reason why, which you're going to study through the chapter here. So let's get some experience. We're going to take a look at a variety of different situations here, and we're going to try to take a real situation, a variety of real situations, and model it with a graph. All right, so the first one here is called is my friendship example. Try to kind of make it real here. So Moose knows Meg, and Ginger, Betty, and Betty. So Moose knows three people: Meg, Ginger, and Betty. Jughead here, he knows. Jughead has. I gotta fix the spelling. Jughead knows Ginger and Betty. Archie has ever only known Veronica. Okay, I'm sorry about the terrible spelling in here. I've got to fix a few things here. And then Reggie here only knows Betty. Okay, so here we go. Our people here are going to be representing, or the vertices are going to be representing each person here. Okay, so I'm going to assign the people as the vertices, and I've got Moose here, so I'm going to put Moose here. And I don't know. You can line them up any way you want. I'm going to put Jughead here. Okay, let's put this vertex here, Archie here. It doesn't matter where you place the vertices here. You just kind of go for it. Now, Moose knows Meg. So right here. Guess what? Our relationship. Oops, that should be a G here. Our relationship that we have between these people here is going to be represented by an edge. All right, so these represent, let's do it in red, the relationship. It shows who knows who, basically. Okay, so the connection, the edge, shows the relationship between the people. So who does Moose know? So Moose knows Meg, Ginger, and Betty. So how about, let's put Ginger here. Kind of reminds me of Gilligan's Island here. And then, how about over here, Betty? Okay, let's read on. Jughead knows Ginger. So Jughead knows Ginger, so I got to connect these two. All right, and Jughead knows Betty. Okay, down here to Betty. Now Archie only knows Veronica, so maybe Veronica's over here. I don't know. Let's put Veronica over here. Once again, you could draw these graphs many different ways. So Archie and Veronica have a relationship there, and Reggie only knows Betty. So maybe Reggie's down here because he only knows Betty. So there's a relationship right there. And just by looking at this graph, even if you didn't know graph theory, it'd probably be pretty darn easy to tell who knows who if you just use a little bit of common sense. All right, it shows the relationship between people. And so you can use a simple graph using vertices and edges to represent the relationships between people, all right, or their friendships, okay? And that's one possible graph, or one possible way you can draw it to display this kind of information right now. All right, now in a different situation, perhaps there's some information on who played who. Okay, games played. A typical week has the following games being played. So on Monday, Pittsburgh is at DC, New York at Philly, and then Chicago at St. Louis. Okay, so who's playing who? So let's get some let's decide what who is what. So just like the people here, the cities are going to be the vertices, right? The cities or the team. So the city, okay, or the team is going to be the vertex, and then whoever the games played are going to be the edges here. So the games played represents the edges between these two cities. So if I put let's say Pittsburgh here, okay, and I put DC right here, DC, Pittsburgh at DC, they've got a game there. So let's connect them. All right, that shows me that Pittsburgh's at DC playing DC. All right, New York and Philly. All right, New York at Philly. So New York at Philly. So I'm gonna have to put maybe New York over here. Excuse me, New York, and then Philly right here, Philadelphia. So they're playing with each other. So I'm gonna connect these guys right here. New York's at Philly, and then Chicago at St. Louis. Okay, so Chicago at St. Louis. So Chicago here, St. Louis, maybe over here. St. Louis, STL. So STL, St. Louis. So I'm going to have to connect Chicago with St. Louis. Okay. So that's 1, 2, 3. So we got 3 games played there. So now that's on Monday, that is. Okay. Now on Tuesday, we got Pittsburgh at DC. So, ooh, guess what? That's another game. So I've got to have a multiple edge here represent that they're played twice. Okay, so multiple edge here and here. On Wednesday, New York's at St. Louis playing St. Louis. So what do we got going there? So New York at St. Louis, maybe over here, right? And then Philly at Chicago, right here. And then on Thursday, Pittsburgh at St. Louis, right down here. Got to put the sound effects in. New York at DC. So that's over here. There's game there. And then Philly at Chicago. So Philly at Chicago. Ooh, there's another multiple edge. So I'm going to need to put one here. All right, so Philly at Chicago there. Let me see, where was it? Philly at Chicago here. So there is another multiple edge here, here, and here. Okay, so you just got to build the graph as you read it. And then, oh, on Friday, well, it's Friday, right? So you got a lot of games. So Philly at DC. Philly at DC. So where's Philly? Philly, and then DC up here. So right up there. Philly at DC. Chicago at Pittsburgh. And then St. Louis at New York. So, oh, there's another multiple edge. So right here. Okay, so St. Louis at New York. And there. So there is another multiple edge right there. So we have 3 pairs of multiple edges. So you just build the graph as you go, and you can look at this drawing, and you can see the games that have played over the week just by looking at the drawing. The drawing doesn't tell you unless you have other information, what day it was played on. However, it does tell you the games played for that week. Okay? Okay. Now on this one here, we got a map of a neighborhood. All right, so the question is, Neighborhood Watch wants to be able to patrol. Oh, the patrol problem. Okay, like you're a policeman. Each block in the community after a rash of burglaries. All right, so he's got to cruise around the streets here. So this shaded region here is the street, right here, and then you've got these blocks right here. You're gonna go around the block, and there's a bunch of houses on each street here. So how do we model this? Well, what we're going to do is we're going to let the edges represent the roads, okay, or the streets. The roads are the streets, and the vertices are going to be the intersections, okay, like right here. Okay, remember this shaded area, these are just streets, and these white squares, they're not houses, they are a full block of houses all together. So there's multiple houses along the street, okay, a lot of them. I don't know how big the block is, but there's a lot of them. All right, so the vertices represent not the houses, but intersections. Intersections. Okay, so like here and here and here and here and here. These are all intersections, right? You're familiar with that. You guys are 17 and 18. You've been in a car a lot, right? Some of you guys even drive. So these are intersections here. So the patrolman has to cruise down here and here. All right, and here and here, here, along every street, right? Because you can't leave out any of the houses because you got to patrol every street. All right, so you don't miss the houses. And so what we got here is a set of vertices. Okay, now let me put the vertices in blue. Right here, which represent the intersections, and then you've got these edges in red represent these streets. Okay, and this becomes the model. So if we take this right over here, let me find my cursor right here, and we just drag this right over here, you'll see our model. Okay, this is the model of the neighborhood. Okay, so the again, this right here is the intersection, right? And this is the road or the street. All right, and then this becomes the model. So we model it with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 15 vertices and a bunch of edges, okay? And this right here looks like our basically our map of our neighborhood. And the question is, what route should he take, all right, to minimize his distance traveled and time traveled through the neighborhood? Okay, that's the problem we'll solve later on. Is it possible? And what is our shortest route? What is the shortest route? That right there, my friends, will be coming up. Okay. Number 4. So after the patrolman comes the mailman. All right. The mailman does the same sort of thing, but he has a different purpose. He needs to figure out a delivery route for the same neighborhood. Assume that there's a mailbox in front of each house, and assume that he needs to drop off the package at the doorstep of each house. Hmm. Hmm. Okay. So now this is important here, okay? Because so what's going to happen is this: since we deal with a mailman, okay, there's these once again, these shaded regions are streets, and you got houses along here. You got houses here, 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 and here. You got houses here too, and here, and here, and here, and you got houses along these blocks right here. So the mailman has to cruise down the street on both sides. Okay, so the mailman, this is important. This is different than the patrolman. The patrolman just has to go down the street and he can patrol both sides just by looking. But the mailman, that's different. The mailman has to travel, okay, both sides. Okay, keyword both. Why? Because he's got to get both houses, right? Houses are on both sides of the street. Well, some streets, not all. Over here, not. Over here, not. But in between these blocks, yes. Okay. So both sides of the street, assuming that there are houses on both sides. Okay, so you have to look at the diagram for that. So the key word is both sides whenever there's houses on both sides. So let's cruise that. So right here, one edge only because there's only one side of the street that has houses. Okay, on the top up here, only one side of the street has houses. One side of the street only has houses here. Here, there's two sides of the street that has houses, so he's going to have to traverse it twice. So you're going to need two edges there. Only once here, because there's only one side here, one side here. Oh, here are two sides. One side here, here two sides, here two sides, here one side, and here two sides, one side, one side, one side, one side. Here two sides, here two sides, here one side, and here's one side. So when we take a look at this model, when you take this and basically recreate it off to the side, you have a model. Oh, what happened here? This one and this one's missing. Okay, I'm talking about right here and here. Okay, you have this model. So this becomes our model, all right, for the mailman. And this tells me the path that he has to take, or it gives me the streets that he must has to take, or the number of times down each street that he has to make in order to deliver mail to both sides of the street and wherever their house is. Okay, so model for the mailman. So the mailman problem is different than the patrol person, because the patrolman, if he's walking down the street, he can see both houses, and so he doesn't need to traverse it twice. Traverse meaning go up and down. The mailman does, because he's got to go both sides of the street, because there's houses on both sides of some of these streets. So you got to be careful on how you interpret each problem, because each problem is different. The mailman and the policeman, slightly different problems. Okay, this next one here. So check this out. So we've got a map here, obviously, representing different zones for high schools, and which zone borders each other for the 2009-2010 WSFCS school year. All right, so how do we model this situation here? So what we need to do, this is the same map, by the way. I just um, recreated it twice. What we're going to do is we're going to let the excuse me, we're going to let the high schools be the vertices, okay? And we're going to represent the edges as those high schools that are bordering in the cities, okay? So edges represents the who borders who, okay? Who's border meaning who's next to. All right, so I'm going to use a bigger graph because it's a little bit easier to see. Okay, and then I'll reconstruct it over here. So we've got North Forsyth up here. So this is high school, okay? So North Forsyth, so F, North Forsyth. And then right here we got Reagan, R. And then over here we got Mount Taylor, MT. And then up here we got Carver, C. And then over here we got East Forsyth. Ooh, East Forsyth. And over here we got Atkins, A. And I'm just symbolizing the vertices, right, using the initials. And then over here we got West Forsyth. And right here we got Parkland, P. And over here we got Glen. Okay. All right, so we got these vertices represented, the vertices represent our high schools. So vertices equal high schools. And then if they border each other, we're gonna use an edge to indicate that. So if they border one another, if they're next to one another, if they have a common border, there's going to be an edge between these two high schools. So I noticed that right here, looking at the map here, that North Forsyth borders Carver. So I connect the two because that shows me that they border one another. I also noticed that North Forsyth borders Reagan. And North Forsyth, the pink and green here, they border one another too. So they border Mount Tabor. Okay. And ooh, there's a little connection here between orange and green, because so that means Carter borders Mount Tabor. Okay. Now the orange and light blue here, East Forsyth and Carver, they border. Atkins clearly borders Carver. Carter right here, or Atkins, excuse me. Atkins borders Reynolds, and Reynolds borders Mount Tabor. You see how it works right now? And then Mount Tabor borders Reagan, and Reagan borders West Forsyth. And West Forsyth and Reynolds, they border one another here. And Parker borders West Forsyth and Reynolds. Oh, and Atkins. Whoa, and Glenn. And Glenn obviously borders East Forsyth. Oh, and Atkins. Okay, right there. And see what else. Did I miss anything? Oh, yes, I did. Reynolds. See, purple and orange, they border one another right here. And then, Reynolds and Reagan, they border one another right there too. Okay. And so hopefully I didn't miss one here. So that's the tricky part. You gotta keep track of your borders here. So the borders are the edges, who borders who, and vertices are the high schools. All right. And if you take this, let me grab this model here that I created, overlapping your map here. You can see the model really well if I just pull it off to the side. So this is the model of the high schools of who borders who. Oh, I missed one. Adkins borders East Forsyth right here. So I missed one. So I'm going to put that in right here. Okay, missed one there. That should have been obvious to me. So this here's the model of the cities, of how the cities border one another, of how the cities border each other. And then we can go from there and analyze other things. So the very first step in problem solving is learning how to model, taking a real life situation and interpret it mathematically through a graph or a function or something like that. And then after that, you got to solve a problem, solve some realistic problem. And you're going to see that coming up, okay? But in this lesson, you're going to learn how to take real situations, model them with a graph, and then later on we work with the graphs that we create to solve bigger and better problems, okay? Now your problems, I want you to try. There's down here, obviously this is your homework. All right, so try this. All right, obviously in your book here, page 187, 15, 17, 19, 20, and you're going to be modeling real life situations by using a graph, okay? Which is just a bunch of edges and vertices. All right, and then in our next lesson here, what do we got coming up in section 5? Ooh, we got some major theorems coming up. So this is a big lesson. We've been building up to this, and here it comes, okay? So remember, this is a video, right? And if you need to, you can go ahead and go back to the beginning if you like. This is section 5.4. And if I went too fast, go ahead and rewind it and check it out and listen to it one more time, just so you can fully understand what's going on. All right, this is Mr. Ainsworth. I will see you in my next lesson here in section 5 coming up here. We'll talk about Euler theorems. I'll see you then.